Assalamu alaikum guys, welcome back. Okay, so now lecture 17 of this chapter and of AS chemistry crash course, and now we are gonna move on to the second subsection of this chapter, which is known as covalent bonding. Okay, we've done ionic bonding so far and now we are gonna do covalent bonding. Okay, so first of all, let me explain what covalent bonding is. It's the same concept as the one which you guys did in your O levels. Covalent bonds, how are they formed? These are basically the forces of attraction, or these are the bonds which are made by the sharing of electrons between non-metallic elements. Okay, so bonding formed by sharing of electrons. There is no transfer of electrons in here. Okay, it's sharing. By sharing of electrons between non-metallic elements. Okay, this is a key term, non-metallic elements. It does not form between metallic elements, it's formed only between non-metallic elements. Okay, and in case of covalent bonding we have to share electrons. Okay, and the basic concept of O levels apply. Now for example, if you have to form a covalent bond, and this is for example your molecule chlorine Cl2. So chlorine is in group 7, and this chlorine molecule which is made, how are we gonna form this molecule? Because this chlorine, if it exists in the form of an atom Cl, then its outermost shell would have how many electrons? Since it's in group 7 or group 17, it has only 7 electrons. It needs 1 electron, and the other chlorine atom also needs 1 electron. So if both the chlorine atoms, they share electrons, they share one electron with each other, then of course both of them will have 8 electrons. So I'm drawing dots to represent the electrons of one chlorine atom, and I'm drawing crosses for one and dots for the other, the electrons of the other chlorine atom. Okay, and now this electron is shared. Okay, now this pair of electron that is in the middle, this is shared by both of them. Okay, you don't need to draw a circle over here, by the way. If you are asked to draw the dot and cross diagram of anything, of any molecule, this is how you're going to do that. Okay, represent the dots for being the electrons of the one and crosses to be the electrons of the other. You don't need to draw the shells over here. Okay, the shells were necessary in your O levels but not in your A levels. Okay, similarly if you want to draw out HCl, H and Cl, so again crosses, and then this is cross, and then this is the dot that hydrogen has. Hydrogen has the only 1 electron in its outer shell, in its duplet, so it has to share that electron with chlorine in order to stabilize itself and get 2 electrons in its shell. So its duplet is stabilized in case of hydrogen, and in case of chlorine the octet is stabilized, and you guys already know all of this stuff. Now before we move on into further details of covalent bonding, now a very important concept of electronegativity needs to be discussed first. So let's move on to electronegativity. Alright, so what is electronegativity? Electronegativity by definition is actually an ability of an atom to pull a bonded electron density towards itself. Now I'll give you an example. For example, I have hydrogen and chlorine bonded to one another, hydrogen chloride or HCl, hydrochloric acid, and there is a covalent bond in between them, right? A single covalent bond, and you guys know that a stick also represents a covalent bond. Now the electrons which are here in this covalent bond, let me just draw them out for you. Now these electrons which are here, they are being pulled continuously by the nuclei of the 2 bonded atoms. Okay, by the nuclei, because the nucleus of chlorine has a positive charge, right? Has a positive charge, and so does the nucleus of hydrogen have, right? Now what these nuclei would do, since they are positive and the electrons which are shared are negative, these positively charged nuclei will try to pull the electrons towards themselves, and as a result these electrons are not gonna be midway or halfway between them, but rather this electron density will be shifted towards the stronger pull side, right? So first of all, this pull or this relative ability to pull on the bonded pair of electrons is called electronegativity. Clear? This is the definition of electronegativity, that the relative ability to pull the bonded pair of electrons towards itself is known as electronegativity. If we are pulling some free electron, and that ability is not going to be electronegativity, okay, the pull on the bonded pairs is going to be your electronegativity. First of all, this was the concept of electronegativity. I'll just quickly note it down over here. What is electronegativity? It is the relative ability of the bonded atoms to pull the electrons, or the electron density, or the bonded electrons, I should say, the bonded electrons towards themselves. Bonded electrons towards themselves. Okay, so this is what electronegativity actually means. Now the electronegativity of all the atoms is not equal. It changes from atoms to atom. So now let's look at the trend of electronegativity across the periodic table. Okay, what's the trend of electronegativity across the periodic table? Okay, so for example, this is our periodic table over here, a small periodic table. Okay, let me just erase this out. Okay, a small periodic table over here. Now these are the end. Now, how does the electronegativity change in this periodic table? First of all, you should know what the electronegativity depends upon, the factors on which the electronegativity actually depends upon. So electronegativity actually depends upon two factors, which are collectively termed as in the form of a third factor, but I'll first discuss the two factors. First of all, this pull on the electrons has to depend upon the nuclear charge, because it's the nucleus that is attracting the electrons towards itself. So the first factor is the nuclear charge, or I should say the proton number basically. And the second factor is the atomic radius. Okay, why am I saying atomic radius? Because see, if the radius is small, then that means the charge is going to be more compact, and if the charge is compact, then the pull on the electrons is going to be stronger. But if the radius is large, then the nuclear charge is going to be a bit not compact, meaning it's going to be a bit distributed, and if it is, then of course the pull is going to be weaker. Okay, so somewhat like that. So it's actually not the radius alone on which it depends, but yeah, radius is one factor, not on the nuclear charge alone on which it depends, but still nuclear charge is also a factor. Both these factors are collectively explained in a third factor, which is known as charge density. Charge density. Now charge density by definition is actually the charge per unit volume. Okay, by volume I mean the radius. Okay, because the radius depends upon the volume, or the volume depends upon the radius, right? So the charge density is actually proportional to the electronegativity. The charge density is proportional to electronegativity. So the higher the charge density, the greater the electronegativity. The lesser the charge density, the lesser the electronegativity. Now, if the formula for charge density is the charge per unit volume, meaning charge divided by volume, then that means if the nuclear charge, and by the way, this is the nuclear charge, okay, the proton numbers inside the nucleus. If the nuclear charge increases, then the charge density has to increase. And if the charge density increases, then of course the electronegativity has to increase. And what about the volume? It's inversely related to the volume, because volume is in the denominator. So now, if the volume decreases, then that means the denominator is going to become smaller. If the denominator is going to become smaller, then the charge density will rise, and if that rises, again electronegativity will rise. So it's actually the charge density on which the electronegativity actually depends upon. Okay, so charge density actually gives you an idea of the distribution of the nuclear charge across the nucleus basically of that atom. So This is what you should remember. This is the key term. The charge density is on which the electronegativity actually depends upon. Okay. So now, according to this phenomena, this rule, what should be the trend? We have to keep both of them in mind. So as we go up the group, what's happening? As we go up the group, the atomic radius is falling. It's going to decrease because the shells are becoming smaller and smaller and smaller as you go up the group. So if the radius is decreasing, then the charge density will rise, and if charge density will rise, then of course electronegativity has to rise. Okay. I know proton number will fall as well, but the decrease in factor will impact more on the charge density than the proton number. Okay. Now, after this comes across the period from left to right. Okay, what's happening from left to right? Remember the trends video I made in the previous videos? As we go from left to right, the atomic radius shrinks in size. Again, radius has to shrink. And if the radius is shrinking, and not just the radius is shrinking, but the proton number is also increasing. Okay, as you go across the period, the proton number increases, meaning the nuclear charge is increasing. So what's happening? There is a double effect, meaning the numerator is increasing and the denominator is decreasing. That means the charge densities has to rise. It has to rapidly rise as we go across the period. Therefore, electronegativity will also shoot up as we go across the period. And by the way, the electronegativity of group 8 elements is ignored. Okay, we do not talk about that in our periodic trends because they are noble gases, they are already stable, so we don't need to talk about them. So it's a fluorine till which we are going to talk. And as you go across diagonally, basically as you go diagonally across the periodic table, what's happening? As you go diagonally, again electronegativity is rising. Why am I saying that? Because going diagonally actually means going up the group and across the period. Simple as that. And if you're going up the group and across the period, then that actually means the electronegativity is rising again. So if I were to ask you to tell me the most electronegative element of the periodic table excluding the noble gases, then it's going to be fluorine. Okay, fluorine. This is the most electronegative element of the periodic table. And what's the least electronegative? It's going to be cesium. Cesium of group 1. Okay, not francium because it's radioactive and we do not talk about francium. Okay, so cesium to fluorine. So this was the trend of electronegativity and the concept of electronegativity. Okay. After this, we are going to talk about polarity and then we are going to talk about dipoles and partial charges. Thank you.